Welcome to LLMs with a Library Card, an introduction to Recursive Language Models, or RLMs. The big idea is simple. Instead of asking a language model to hold everything in its head, we give it a reliable way to look things up, like checking out books from a library when it needs facts, context, or supporting evidence. In this presentation, we'll explore how recursion lets a model break a task into smaller steps, retrieve the right information at each step, and then combine those pieces into a stronger final answer. This overview is based on the paper Recursive Language Models by Alex L. Zhang, Tim Kraska, and Omar Khattab from MIT CSAIL. Modern language models run into a problem often called context rot. The longer the input, the worse their answers tend to get. Even frontier systems can lose accuracy quickly as the context window grows because they struggle to keep the right details active and prioritized. That becomes a major barrier for long horizon work, like analyzing lengthy documents, tracing decisions across many chapters, or handling workflows that span tens or even hundreds of millions of tokens. The cartoon captures it well. Ask a simple question about something mentioned early in a massive book, and the model gets overwhelmed, guesses, and quality degrades. In short, more context doesn't automatically mean better understanding. Performance in long context settings doesn't gradually taper off, it can drop off a cliff. Here they tested GPT-5 on 3 long context tasks that get progressively harder: O-long pairs in green, O-long in orange, and S-NIA in blue. The y-axis is score, and the x-axis is input context length on a log scale. Notice what happens as the tasks become more complex. The model's effective context window shrinks. On the easier S-NIA task, performance stays high even as context grows. But for O-long, and especially O-long pairs, accuracy collapses much earlier, even well before the marked GPT-5 context limit. The takeaway is that context length isn't the same as usable context, especially on harder reasoning. What if, instead of cramming everything into an LLM's context window, we treated the prompt like an external environment the model can interact with? That's the key insight here. Long prompts don't need to be fed directly into the transformer all at once. Instead, the model should be able to symbolically access and navigate the information it needs when it needs it. This idea is inspired by out-of-core algorithms, systems with limited memory that still handle massive datasets by carefully fetching the right pieces at the right time. On the left is the old way, forcing a gigantic prompt into a fixed context window. On the right is the RLM approach. Give the LLM tools to explore the prompt rather than swallow it whole. RLMs work by turning the prompt into something the model can actively explore inside a programming environment, like a Python REPL. The entire prompt is stored as a variable, and then the model writes small bits of code to understand and solve it. It can quickly peek at the beginning of the prompt, say, printing the first 100 characters, so it knows what it's dealing with. Next, it decomposes the request into smaller, manageable pieces. Finally, it can delegate those pieces by calling itself recursively, like an LM query that asks a focused question such as, find items in Chapter 1. The root RLM acts like a boss, and the subcalls return targeted sub-responses that get assembled into the final answer. Here's the key takeaway. Reinforcement-learned models keep working in regimes where the base model falls apart. They repeated the same scaling experiment, but this time with RLM built on GPT-5. On the left, the base GPT-5 starts strong at shorter contexts, then performance drops sharply as inputs get longer, especially on the more demanding oolong and oolong pairs tasks, until it essentially collapses. On the right, RLM GPT-5 tells a very different story. Scores stay high and remarkably flat across context lengths, even as they push all the way to around 1 million tokens. In other words, the RLM remains stable and robust, handling inputs up to 2 orders of magnitude beyond the base model's context window. What's surprising about this approach is how affordable it can be, often comparable to, or even cheaper than, calling the base model directly. The reason is simple. An RLM can selectively pull in just the context it needs instead of ingesting everything up front, so the typical or median cost is often lower. You can see that around the middle percentiles, the RLM tends to come out ahead. The trade-off is variance. Costs can spike when the RLM gets curious and runs extra steps to explore, verify, or search for a better answer. That's why the upper tail, like the 95th percentile, can be noticeably higher than the base model. Two core features of RLMs solve two very different challenges: length and complexity. First, the REPL environment is what makes long inputs practical. Instead of forcing everything into a single context window, the model can interactively access information as needed, even at massive scales like millions of tokens. Second, recursive subcalling is what makes dense, messy problems tractable. When a task has quadratic or combinatorial structure, like many pairwise comparisons, trying to solve it in one pass quickly becomes overwhelming. Recursion lets the model break that tangled problem into smaller subproblems, solve them one by one, and then combine the results. In short, the REPL helps us reach more information, and recursion helps us reason through it. The big takeaway here is simple. LLMs become fundamentally more powerful when you give them tools. On their own, models can suffer from what we call context rot, where performance drops as inputs get longer and more complex. The solution is to shift how we use the model. With RLM, the prompt is treated like an external environment the model can explore, using code, intermediate steps, and even recursive self-calls to navigate large or messy information. And the result is compelling. Orders of magnitude improvements in effective context handling, stronger performance on complex tasks, and costs that are comparable, sometimes even lower, than traditional approaches. If you'd like to go deeper than the highlights in this presentation, the full paper is available on Archive by original researchers. It's titled Recursive Language Models by Alex L. Zhang, Tim Kraska, and Omar Khattab from MIT's Computer Science and Artificial Intelligence Laboratory. You can also access it using the link shown at the bottom, arxiv.org/pdf/25112.24601. Again, thanks to the researchers for their hard work. The paper includes the full technical details, experiments, and implementation insights behind the approach, so it's a great next step if you want to explore the method more rigorously. See you in next video.